Good day, everyone, and welcome. Today, we delve into the fascinating world of autonomous vehicles with our paper, MoST, Multi-modality Scene Tokenization for Motion Prediction. We're exploring a groundbreaking approach to enhance motion prediction, addressing critical safety scenarios like U-turns and cyclist crossings. Stay tuned as we unravel how our method, MoST, outperforms existing models and paves the way for safer autonomous navigation. Let's get started. We've introduced a novel method, MoST, which significantly improves motion prediction in autonomous vehicles. This method efficiently combines symbolic representations with scene tokens that encode multi-modality sensor information. This innovation was driven by the limitations of existing models, such as MTR, Waveformer, Multipath++, Motion CNN, Motion LM, and Scene Transformer, which struggled to predict accurate trajectories in complex scenarios. For instance, these models had difficulties predicting U-turns or situations where a cyclist might cross the street. Our MoST method addresses these challenges, providing a more robust and accurate solution for motion prediction in autonomous vehicles. Our research introduces a novel methodology, MoST, which utilizes sensory tokens from LiDAR and camera inputs. This approach applies a single decoder for LiDAR and camera tokens, and 3 decoders for camera tokens alone. During inference, we fit a Gaussian mixture model by merging predictions from these decoders. We draw 2048 samples and aggregate them into 6 trajectories using k-means. In terms of performance evaluation, we compared our approach with recently published models. The introduction of sensory tokens led to a clear performance gain over the Waveformer baselines. Notably, our approach achieves state-of-the-art performance across various metrics. This demonstrates the effectiveness of our methodology in improving motion prediction models. The core motivation of our research is to enhance motion prediction in autonomous vehicles. We identified a problem in the current landscape. Existing models often struggle with complex scenarios. This is not just a technical issue, but a safety concern as well, as inaccurate predictions can lead to hazardous situations on the road. To address this, we developed the multi-modality scene tokenization, or MoST method. As you can see in the figure, MoST takes multi-view camera images and a full scene point cloud as input. It then uses a pre-trained image foundation model to obtain descriptive feature maps. The scene is decomposed into disjoint elements via clustering, and each point is assigned a token or cluster ID. Box information for each element is derived, and finally, one feature embedding for each scene element is extracted. This innovative approach allows us to better understand and predict the complex behaviors of agents in a driving environment. While previous solutions have shown promise, they often struggle with complex scenarios, fail to rule out unsafe possibilities, and lack the ability to predict safety-critical behaviors. To address these limitations, we introduce a novel method called MoST, or multi-modality scene tokenization. MoST enriches transformer-based models by incorporating scene tokens, which encode multi-modality sensor information. These tokens are derived from sensory inputs such as LiDAR and camera data, providing a richer context for motion prediction. The innovation in MoST lies in its unique approach to decoding. We use a single decoder for LiDAR and camera tokens, and 3 separate decoders for camera tokens alone. During inference, we fit a Gaussian mixture model, which allows us to merge predictions from the decoders and draw samples. This approach has led to significant performance gains and state-of-the-art results across various metrics. In essence, MoST is a leap forward in motion prediction, providing a more comprehensive and accurate understanding of complex scenarios. Our research introduces a novel method known as MoST, or multi-modality scene tokenization. This technique enriches transformer-based motion prediction models by combining symbolic representations with multimodality scene tokens. MoST utilizes sensory tokens derived from LiDAR and camera inputs. We use a single decoder for LiDAR and camera tokens, and 3 decoders for camera tokens alone. During inference, we fit a Gaussian mixture model by merging the predictions from these decoders. We then draw 2048 samples and aggregate them into 6 distinct trajectories using k-means. This method significantly enhances the accuracy of our trajectory predictions. In essence, MoST is a powerful tool that leverages multimodality sensor information to improve motion prediction models, making it a valuable asset in the field of autonomous vehicle technology. Our research introduces a novel method known as MoST, or multi-modality scene tokenization. This approach is versatile and can be applied to a variety of transformer-based motion prediction architectures. For the purpose of our study, we used Wayformer as our baseline model. We then compared MoST's performance with several recently published models, including MTR, Wayformer, Multipath++, Motion CNN, Motion LM, and Scene Transformer. The results were clear. MoST consistently outperformed these models in predicting accurate trajectories in complex scenarios. For instance, with tokenized sensor information, MoST was able to rule out the possibility of a vehicle running into walls after making a U-turn. In another example, MoST predicted that a cyclist might cross the street, a critical piece of information for an autonomous vehicle to take precautionary measures. In essence, MoST enriches the information fed to motion prediction models by efficiently combining existing symbolic representations with scene tokens that encode multimodality sensor information. This leads to a clear performance gain and sets a new standard in the field. Our multimodality scene tokenization, or MoST, has shown impressive results in predicting complex trajectories. It's able to rule out unlikely scenarios, such as a vehicle running onto walls after a U-turn, and can predict safety-critical behaviors. This is crucial for autonomous vehicle safety, as it can anticipate a cyclist crossing the street, allowing the vehicle to take necessary precautions. The introduction of sensory tokens from LiDAR and camera inputs has significantly improved performance. When compared to the Wayformer baselines, the use of these sensory tokens has led to a clear gain in performance. But the achievements of MoST don't stop there. It has outperformed existing models, achieving state-of-the-art performance across various metrics. This makes MoST a promising approach in the field of motion prediction, setting a new standard for future research. Our technical results have significant implications for the field of autonomous driving. Firstly, our model's ability to predict complex trajectories enhances the reliability of autonomous vehicles, making them more capable of navigating in diverse environments. Secondly, our model's understanding of physical constraints allows it to rule out unlikely scenarios, such as a vehicle running onto walls after a U-turn. This demonstrates a nuanced understanding of real-world conditions. Furthermore, our model's ability to predict safety-critical behaviors, like a cyclist crossing the street, allows for improved safety measures in autonomous vehicles. This is crucial in ensuring the safety of all road users. In terms of performance, our approach shows a clear gain over the Wayformer baselines when we introduce sensory tokens. This suggests that integrating sensory data can significantly improve motion prediction models. Finally, our approach achieves state-of-the-art performance across various metrics, suggesting that our method, MoST, could potentially set a new benchmark in the field of motion prediction. This is a promising step towards creating more reliable and safer autonomous vehicles. We've introduced a novel method called MoST, or multi-modality scene tokenization. This approach leverages sensory tokens from LiDAR and camera inputs to significantly improve motion prediction in autonomous vehicles. As you can see in the figure, MoST outperforms the Wayformer baselines in predicting complex trajectories, such as a vehicle entering an unmapped plaza. It also excels in predicting safety-critical behaviors, like a cyclist crossing the street. This demonstrates the superior performance of MoST in handling real-world scenarios, making it a promising tool for the future of autonomous driving. Our multimodality scene tokenization, or MoST, is a versatile tool. It can be applied to most transformer-based motion prediction architectures, demonstrating its wide applicability. When we evaluated its performance, we compared it against recently published models. The results were clear. MoST showed a significant performance gain over the Wayformer baselines. But what makes MoST so effective? The answer lies in the use of sensory tokens. These tokens have led to a significant improvement in motion prediction, enhancing accuracy in complex scenarios like U-turns or a cyclist crossing the street. Finally, MoST contributes to sensor-based motion prediction by enhancing the waveformer with camera embeddings. It also creates a large-scale multimodal dataset for benchmarking. This is a significant step forward in the field, and we're excited about the potential applications of this technology. Our research has led to significant advancements in the field of autonomous systems. We've developed a method that integrates multimodal sensor signals to represent multi-frame scenes as a set of scene elements. This approach encodes rich semantic and geometric information for each element, providing a comprehensive understanding of the environment. Moreover, our method is capable of predicting safety-critical behaviors, such as a cyclist crossing the street. This ability to anticipate potential hazards enhances the safety of autonomous vehicles, making them more reliable and efficient in complex environments. In conclusion, our work represents a significant step forward in the development of autonomous systems, combining multimodal sensor data and advanced prediction models to improve safety and efficiency.